Hello everyone. Welcome back to Factory Discovery. Today we'll discuss about very interesting topic, the amazing process behind millions of glass beads made in modern factories. Part 1. The hidden world behind a tiny object somewhere on a jewelry counter in a small town in Ohio. A woman picks up a bracelet and admires the way the light catches a single glass bead, no bigger than a grain of rice. She has no idea what she is actually holding. She sees color and shine, a small decorative object worth a few cents, easily overlooked, easily replaced. What she does not see is the furnace that once burned hotter than lava to create it, the molten river of liquid glass that had to be tamed into a perfect sphere, or the small army of workers and machines that turned raw sand into something beautiful enough to sit on her wrist. Every single year, factories around the world produce billions of these tiny objects, more glass beads than there are people on the planet, and almost none of us ever stop to ask how something this small could possibly demand a process this complicated. Today we are stepping inside that process. We are going to follow a glass bead from its very first ingredient, a pile of ordinary sand, all the way through fire, pressure, color, and precision, until it becomes the finished object sitting in a jewelry box or sewn onto a designer's dress. This is not a small story. It is an enormous industrial operation hiding inside something you could lose in your carpet, and by the end of this journey, you will never look at a simple string of beads the same way again. Part 2. Where a bead actually begins long before anything resembles a bead. The process begins with something almost embarrassingly ordinary, sand. Not beach sand though. Manufacturers need silica sand, a specific type mined from quarries prized for its purity, because even tiny impurities like iron can leave an unwanted tint in the finished glass. Trucks haul this sand into massive storage silos at the factory, where it waits to be blended with two other essential ingredients, soda ash and limestone. Soda ash lowers the melting point of the sand, since pure silica alone would require temperatures too extreme and too expensive to work with efficiently. Limestone, meanwhile, adds durability, helping the finished glass resist the kind of chemical breakdown that would otherwise leave beads cloudy or brittle over time. In many modern factories, a fourth ingredient joins the mix, recycled glass known as cullet, crushed and cleaned scraps from broken bottles, discarded glassware, or leftover material from earlier production runs. Adding cullet does something remarkable. It actually reduces the amount of energy needed to melt the batch, since recycled glass liquefies faster than raw sand. Workers carefully weigh out each ingredient according to a precise recipe, because even a small imbalance can change the color, clarity, or strength of the beads produced hours later. Once measured, the ingredients are mixed together into what the industry calls a batch, a dry, sandy blend that looks utterly unremarkable, giving no hint of the transformation it is about to undergo. Part 3. Into the furnace. The batch is fed into a furnace that runs continuously, 24 hours a day, 7 days a week, because shutting it down and restarting it would waste enormous amounts of energy and risk damaging the furnace lining itself. Inside, temperatures climb past 1500 degrees Celsius, hot enough to make the sand, soda ash, and limestone forget their separate identities entirely and merge into a single glowing, molten liquid. Watching through the small viewing ports built into the furnace wall feels almost otherworldly, an orange river of liquid fire shifting and rolling like something alive. The heat radiating from these furnaces is intense enough that workers stationed nearby wear specialized protective gear, and even brief exposure without it could cause serious burns in seconds. As the raw materials melt, trapped air bubbles rise slowly to the surface in a process engineers call fining, and if this step is rushed, the finished beads will carry tiny imperfections, cloudy pockets that catch the light in all the wrong ways. Depending on the furnace design and the batch size, this melting and refining process can take anywhere from several hours to an entire day before the molten glass is judged pure enough and consistent enough to move forward. It is a strange thought that something as delicate as a bead spends its earliest hours as a churning, superheated liquid, indistinguishable from lava, patiently waiting for the moment it will be pulled, shaped, and cooled into something small enough to fit. On a fingertip. Part 4. Giving liquid fire its shape. Once the molten glass reaches the right consistency, it has to be shaped, and manufacturers rely on a handful of different techniques depending on the type of bead being produced. In one of the oldest and most widespread methods, workers or machines draw the molten glass out into long, thin canes, essentially glass spaghetti stretched and pulled at controlled speeds until it reaches the precise diameter required for the finished bead. These canes can stretch for astonishing lengths, sometimes hundreds of meters, cooling gradually as they travel along a track before being cut into short segments. In a different technique used for rounder, more uniform beads, a technique called mandrel winding, a thin metal rod is dipped directly into the molten glass and rotated continuously, wrapping the glass around itself in layers the way you might wind string around a spool, building up a perfectly rounded shape before the glass has any chance to cool unevenly. Larger operations increasingly rely on automated forming machines that can produce astonishing volumes, spinning out thousands of uniform beads every single hour with barely any human intervention beyond monitoring the equipment. Whichever method a factory chooses, the underlying challenge remains the same. Molten glass wants to move, sag, and drift out of shape the instant it leaves the furnace, and the entire forming process is really a race against gravity and cooling time. A narrow window in which liquid fire has to be coaxed into a stable, symmetrical form before it hardens into something permanent. Part 5. The moment of the cut with the glass now shaped into canes or wound onto rods, it faces its next transformation, being cut down into individual beads. For cane-based production, the long glass rods pass through high-speed cutting machines fitted with precision blades, slicing the cane into short, cylindrical segments at a pace almost too fast for the human eye to follow, sometimes producing thousands of raw beads in a single minute. These freshly cut pieces are not yet round, though. Many still carry sharp edges and flat-cut faces, closer in shape to a tiny cylinder than the smooth sphere most of us picture when we think of a glass bead. To solve this, factories use a secondary tumbling process, loading the rough beads into large rotating drums, sometimes alongside fine abrasive materials, allowing the beads to collide gently with one another and with the abrasive medium over an extended period. This constant, controlled friction slowly wears away sharp corners and smooths rough surfaces, gradually coaxing each piece toward that familiar rounded shape. Heat plays a role here too, because many beads pass through a secondary reheating stage, briefly softened just enough to let surface tension pull them into a more perfectly spherical form, a technique borrowed from centuries-old glassmaking traditions and refined with modern precision equipment. It is a strange kind of alchemy, watching a machine take something as crude as a chopped glass cylinder and, through nothing more than heat, motion, and time, coax it into a smooth, glowing sphere. Part 6. Color, light, and chemistry. Color is where glass beads truly become art, and the chemistry behind it is far more intricate than most people realize. Some factories introduce color at the very beginning, mixing metal oxide compounds directly into the molten batch before it ever reaches the forming stage. Cobalt oxide produces that deep, almost hypnotic blue found in so many traditional beads. Chromium oxide creates vivid greens. Gold chloride, surprisingly, produces a rich ruby red, a technique glassmakers have quietly relied on for centuries. Other factories take a different approach entirely, forming their beads first in clear or lightly tinted glass, then applying color afterward. Through specialized coating processes, spraying or dipping the beads in pigmented layers that are then cured under controlled heat to bond permanently to the glass surface. For beads destined for high fashion or luxury accessories, an additional finishing step often follows, a metallic or pearlescent coating applied in whisper-thin layers, sometimes using vacuum deposition technology borrowed from the electronics industry, creating that shifting, iridescent shimmer collectors and designers prize so highly. Quality control technicians inspect color batches constantly throughout this stage, because even a slight shift in furnace temperature or coating thickness can produce a noticeably different shade, and manufacturers producing beads for a specific fashion line simply cannot afford visible inconsistency across a single order. What looks like a simple decorative choice, the color of a bead, actually represents one of the most technically demanding and carefully monitored stages in the entire production line. Part 7. The unblinking eye of quality control before a single bead leaves the factory floor. It has to survive an inspection process that would put most consumer products to shame. Automated optical scanners, often paired with high-resolution cameras and artificial intelligence sorting software, examine beads at blistering speed, checking for size consistency, surface cracks, air bubbles trapped beneath the surface, and color deviation, rejecting anything that falls outside strict tolerances. In many modern facilities, this scanning happens at a rate of hundreds or even thousands of beads per second, an almost impossible task for human eyes alone, yet one that has to be done with near perfect accuracy because a single flaw. Beads slipping into a batch destined for a luxury retailer can damage a brand's reputation far beyond the cost of that one tiny object. Beyond visual inspection, factories also perform mechanical testing on sample batches, checking hardness, measuring how much pressure a bead can withstand before cracking, and testing resistance to everyday chemicals like sweat, perfume, and cleaning products, since beads sewn into clothing or worn as jewelry face constant exposure to exactly these substances. Beads intended for children's products or export to countries with strict safety regulations undergo even more rigorous testing, screening for lead content and other restricted materials, a critical step given how frequently small beads end up in the hands, and sometimes the mouths, of curious toddlers. It is easy to imagine quality control as a minor formality tacked onto the end of production, but inside a serious glass bead factory, it functions more like a relentless gatekeeper, standing between raw industrial output and the polished, trustworthy product a customer expects to find on a store shelf. Part 8. Stringing, sorting, and packaging. Once beads pass inspection, the factory faces a logistical challenge almost as complicated as the manufacturing itself, organizing what can amount to millions of tiny, nearly identical objects into precisely sorted, sellable units. Automated sorting machines separate beads by size down to fractions of a millimeter, since even a slight inconsistency can throw off the tension and drape of a finished jewelry piece. Color sorting happens simultaneously, with optical sensors distinguishing between shades so close that an untrained human eye might never notice the difference. Yet a designer working on a matched collection absolutely would. From there, beads are funneled into packaging lines suited to their eventual use. Some are strung onto temporary cords in uniform lengths, ready to be shipped to jewelry makers and craft suppliers who will restring them into finished bracelets and necklaces. Others are packaged loose by weight, destined for bulk buyers, embroidery workshops, or fashion houses that will apply them directly onto fabric using specialized sewing or gluing techniques. A smaller portion, particularly beads with especially fine detailing or premium finishes, are hand-inspected and individually packaged, a labor-intensive process reserved for beads headed toward high-end boutiques and luxury markets across North America and Europe. Throughout this entire stage, workers and machines move in a carefully choreographed rhythm, because a single mismatched batch shipped to the wrong customer, whether the wrong color, wrong size, or wrong quantity, can unravel weeks of careful production planning further down the supply chain. Part 9. A journey across the world. From the moment a finished batch of beads leaves the factory floor, it enters a global supply chain built to move enormous volumes with remarkable speed. Shipping containers, each holding what might amount to hundreds of millions of individual beads, travel by sea across oceans toward distribution. Hubs in the United States, Canada, the United Kingdom, and across the European Union, journeys that can take anywhere from a few weeks to over a month, depending on the origin, port, and destination. From those hubs, smaller shipments fan out to countless destinations, craft supply retailers stocking shelves for hobbyists, fashion manufacturers integrating beads into clothing lines, jewelry designers building entire collections around